All right, so in this video, we're going to look at the third and final version of the argument that selfish mining, meaning a deviation from the intended behavior in longest chain consensus, can in fact boost the share of the block rewards that's earned by a node running the protocol. So in this video, we will relax, finally, the somewhat unsatisfying assumption we've been making thus far. Remember, thus far, we've been basically, in effect, allowing the deviating node, which we've been calling node A, to, in addition to its deviation, along the way control how honest nodes break ties among competing longest chains. Now, where did that assumption come from? We basically inherited it from Lecture 8 when we were studying the consistency and liveness properties of longest chain consensus. You know, and the motivation there was, right, it's just kind of, it's very hard to justify any specific assumptions about what some, node may or may not be able to do within the communication network. For example, if you're in the synchronous model, okay, no message can be delayed by more than capital delta, but within that sort of, window of capital delta, it seems kind of risky to make assumptions about what one node may or may not be able to do as far as manipulating the order in which messages are delivered. So in the context of Lecture 8, that was a quite, reasonable assumption. We were just trying to have the weakest possible restrictions on Byzantine nodes to make our consistency and liveness guarantees as strong as possible. Now that we're thinking about, a profit maximizing node sort of deviating, away from longest chain consensus, which is being run honestly by all the other nodes. Now, and you saw this in the arguments, it kind of felt like we were abusing that flexibility in tie breaking. So in this video, we're going to assume the opposite. We are going to assume that the tie breaking is not at all under control of node A, and actually we're going to assume it's as bad as possible for node A, which is going to boil down to assuming that honest nodes, when they see multiple longest chains and they have a choice, they're going to extend whichever longest chain has at its tip an honestly produced block. All right, so a few comments. So making this assumption that we're breaking ties in effect in the best case way as far as supporting honesty, and in the worst case way as from the perspective of the deviating node A, this is going to make things more challenging, and you'll see that in this video. The strategy is more complex and the analysis is quite a bit harder than what we did in the previous video. And also the result's going to be a little bit weaker. So it's not going to be the case like it was last video that no matter how small you are, deviating from longest chain consensus is a good idea. In fact, it's only going to be true if you're a sufficiently big node. You don't have to be a 51% node, but you do have to be something more in the ballpark of a 33% node in order for deviating from longest chain consensus to boost your block rewards. But this result still does qualitatively prove the point that at least some things do start going wrong, or at least sort of becoming unexpected in Nakamoto consensus, even before the amount of non-honest hash rate approaches 50%, even when it's just down at something like 33%. And as we discussed in the last video, at the time this was announced in 2013 or so, and again this was from Ayal and Sarir's paper, that took a lot of people by surprise. So like last lecture, we're going to be carrying out an analysis that's parameterized by alpha, which denotes the fraction of hash rate that's possessed by the deviating node capital A. We're going to be assuming that alpha is less than a half. Again, 2 videos ago, if you look at the argument for the 51% node case, you'll see that actually works, or a variant of that works no matter how you do the tie breaking. So we already know what's up when alpha is bigger than a half, so let's think about the case where alpha is less than a half. And like in the last couple of videos, we're going to be thinking about the case where all of the other nodes, the other 1 minus alpha fraction of the hash rate, don't think about profit maximization and just sort of naively follow the protocol as intended. So in other words, the goal here is to sort of understand, is it at least the case that if all of the rest of the hash rate is honest, your best response is to also be honest? Is honesty contagious in that sense? Or in game theoretic terms, is everybody honestly following the protocol? Does that constitute a Nash equilibrium? So before I start describing the strategy, let me just remind you sort of the 2 high-level guiding principles of the strategy we developed last video when we had tie breaking under the control of the deviator. The goal was twofold. Goal number one was for node A to get as many of its blocks as possible into the longest chain. Those are the only blocks that garner block rewards. And in the last video, actually, node A was able to get all of its blocks into the longest chain. Okay, so that was sort of the perfect realization of that goal. And then the second goal, right, because the node ultimately wants to maximize the size of its slice of the pie, and so given that it gets all of its blocks into the longest chain, the only other thing it can do is try to orphan honest blocks off of the longest chain, thereby boosting its share of the overall pie. Now, when the node had 51% hash rate 2 videos ago, it was actually able to orphan all of the honest blocks off of the longest chain. We saw in the last video, it was able to orphan some but not all of the honest blocks off of the longest chain. Specifically, each block that node A created, in addition to being on the longest chain, was deployed in such a way that it knocked out one honestly produced block from the longest chain. So that's what gave us that alpha over 1 minus alpha fraction of the block rewards, which, remember, is bigger than alpha for any alpha bigger than 0. So that's a recap of what was going on last video when node A was actually able to control the tie breaking by the honest nodes. Now, what we're going to see in the scenario in this video is that actually any attempt by node A to try to orphan any honest blocks off of the longest chain automatically introduces a risk that the node A will have some of its blocks orphaned off of the longest chain. So in order to make any progress on goal 2, orphaning honestly produced blocks, we're going to see there needs to be some kind of compromise on goal number 1, i.e. If node A does the strategy we're going to describe, it will not be the case that all of its blocks wind up on the longest chain. Hopefully many of them do, at least from node A's perspective, hopefully many of them do, but as we'll see, it will not be the case that all of them get into the longest chain. Let me give you a little bit more intuition about how this assumption at the top of the slide, why this means there's fundamentally a risk into these attempts to orphan honestly produced blocks. So for illustration, suppose there's currently a fork in the blockchain. So we have 2 nodes, B1 and B2. They're both tips of the longest chain. They both have the same predecessor, the block B. Let's suppose block B1 was produced by an honest node. That is, we're going to call it an H block. And block B1 prime was produced by node A, so we're going to call that an A block. Now, even at the level of this tiny example, we already see why the scenario in this video is going to be a lot more challenging for the deviating node A than the one in the last video, right? Because if this was sort of the blockchain in the previous video, where the node A could control how ties were broken, node A would just be done. Node A would, at this point, be absolutely sure that their block B1 prime is going to wind up in the longest chain. Right, so node A itself, it's only going to bother to extend its own block, so it will extend to B1 prime, not B1. And if node A gets to control how the honest nodes break ties, it's going to control them so that they all also extend the A block B1 prime as opposed to the H block B1. Okay, so already when you have a tie in the longest chain, node A was good to go in the previous video, in the previous scenario. Right, now it's the opposite, actually. Right, so now if the blockchain looks like this thing on the right, node A is actually quite nervous, right? So because it's true that it will still keep trying to extend its own block. It will try to extend B1 prime, but under our new assumption, the honest nodes are going to be in a race against it, trying to extend the honestly produced block B1. And so if what node A was trying to do here was orphan the honestly produced block B1, it's not enough just to produce B1 prime. B1 is not going to be orphaned until node A actually successfully produces a second block, B2 prime, extending B1 prime. Only when node A's chain is strictly longer than all the competition, only at that point will the honest nodes switch to extending the chain of A blocks. That's the only point at which node A can then rest easy. So this shows why any attempt by node A to orphan H blocks is going to be automatically risky to node A. Right, so this blockchain on the right, this is an attempt to orphan an H block, namely to orphan B1. To do that, a prerequisite is you need to create another competing block at the same height. So the node A has already successfully done that. That's B1 prime. Right, but the story is not over. Right, so and 2 different things could happen next. Okay, node A might find the next block, or an honest node might produce the next block. And we don't know. It's probabilistic which of those 2 things is going to happen. If node A winds up producing the next block, B2 prime, extending B1 prime, well then node A is happy. Then B1 actually is orphaned. The unique longest chain is the one with the A blocks. And so everything is good to go from node A's perspective. But another thing that could happen is maybe the next block to be produced was by an honest node. Honest nodes are trying to extend the honest block B1 by our tie-breaking assumption. And so if an honest node succeeds, now node A is in an even deeper hole than they were before. So now for node A to orphan these honest blocks, it's going to have to now extend its chain of A blocks twice. It's going to need a B2 prime and a B3 prime before any more honest nodes are tacked on at the end of B2 in order to flip which is the longest chain. And you got to imagine, like, if this keeps happening, so suppose the honest nodes come up with a B3 and then a B4 before node A comes up with a B2 prime, at some point you figure node A is going to give up. Right, and this is using the fact that we're assuming node A has less than half of the hash rates. Honest nodes, on average, are producing blocks at a higher frequency, at a higher rate than node A. So at some point, once A's chain has slipped sufficiently far behind the longest chain of honestly produced blocks, it should just give up, because it's realistically likely to never catch up ever again. Now, as soon as node A abandons the chain it was growing, all of the A blocks on the chain it was growing are going to be orphaned. So, for example, on the right part of the slide, if node A happens to give up once B2 is produced, well, that means B1 prime is going to be orphaned. So that's what I mean by any attempt by node A to orphan the H blocks also introduces the possibility of orphaning A blocks. And so that's why the analysis is going to be pretty tricky, because we have two sort of complex forces going in opposite directions, and we have to measure which of them does node A more good. Okay, does the benefit of occasionally orphaning H blocks outweigh the cost of occasionally having A blocks orphaned or not? That is going to be the essence of the analysis in this video. The fact that it's unclear which way this cost-benefit analysis is going to go, that also starts giving you an inkling about why, the end result, whether or not this is a good deviation or not, will depend on alpha. So for sufficiently big nodes, it will be a good deviation. For sufficiently small nodes, it will not be a helpful deviation. And that's because the cost-benefit analysis resolves itself in different directions, depending on the hash rate alpha possessed by node A. So to give you a sort of overview of where we're going in the rest of this video, so there's going to be 3 slides. This is going to be slide 1. Right, the last video with the sort of worst case tie breaking, we just needed 1 slide to talk through everything, the strategy and the analysis, etc. Here things are more complicated. The strategy is more complicated. The analysis is more complicated. I'll talk you through the strategy on this slide. It will be somewhat reminiscent of the ones we've been talking about in the last couple of videos, but again, we're going to need 4 cases, not 2 cases, so that'll pretty much fill up this whole slide. Then we're going to have 2 slides of analysis. The first of those is going to be modeling kind of the questions we care about, namely, what is the sort of share of block rewards that's earned by this deviating node A under this deviation. We're first going to sort of set that up as a question fundamentally about Markov chains and talk a little bit about the stationary distribution, the relevant Markov chain, and then on the third and final slide of this video, we'll just go through the final calculations to really characterize for which alphas this deviation actually is profitable to the node. So in the last video, we had 2 cases, basically corresponding to which of node A or the honest nodes was sort of furthest along, had produced a block at the highest height. Here we're going to have 4 cases. We're basically going to want to parameterize just how much node A might be ahead of the honest nodes at any given time. To do that, we're going to keep track of 2 different block heights. H sub p, that's going to be the highest height, the maximum height of every block that's been announced to everybody. Of course, every honestly produced block has been announced to everybody, because that's what honest nodes do. Node A will be selectively releasing announcements of blocks. So all of the publicly announced blocks, the highest height one among those is going to be H sub p. Node A may also have some blocks that are secret, that only it knows about, and if there are any such blocks, H sub s is going to denote the highest height among all of them. Let me just remind you what I mean by a block height. We've talked about it many times, but it's super, super important you remember. So the height of a block in a blockchain is the number of hops that you need to get back to Genesis. Or equivalently, it's the length of the chain that ends at that block. So remember, the end of the longest chain is going to be exactly the block with the maximum height. So for example, h sub p, the maximum height of any publicly announced block, from the perspective of the honest nodes, who know only about the publicly announced blocks, they think that the longest chain is currently whichever one ends at the block that has height h sub p. Node A, meanwhile, may know about blocks at even higher heights. If node A ever chooses to release all those blocks, that will create a new longest chain. So let's move on to the strategy. So in case one, basically node A doesn't have anything going on. So just whatever is the maximum height of a publicly announced block, in case one, that's going to be bigger than any blocks that node A might have kept private to itself. We're also going to say this is the case we're in if there are no secret blocks. Basically, if there's no secret blocks that node A is keeping private to itself, just interpret h sub s as like -1 or minus infinity or something like that. So for example, maybe at this point we just have a simple chain of 3 honestly produced blocks, B1, B2, and B3. All right, so we're dealing with Nakamoto consensus, right? So all of the nodes, and node A in particular, are busy trying to sort of solve these hard crypto puzzles. And as they do that, they have some predecessor in mind. They're trying to extend some particular block that's in the blockchain thus far. So in each of the 4 cases, I'm going to tell you 3 things. First thing I'm going to tell you is exactly which block node A is trying to extend. Secondly, I'm going to tell you, what's going to happen if node A succeeds, meaning it creates a block before any honestly produced block. And then third, I'm going to tell you what is node A's response if it fails, meaning that if some honest node creates a block before it does. So in case one, where the honest nodes in effect are ahead, so here node A is just going to say, you know what, I'm just going to, cut my losses. I'm going to accept that all of the honest nodes on the longest chain are going to always be on the longest chain, and let me at least try to sort of extend that myself. So in this case, node A is simply going to work to extend the longest chain. So the publicly announced block, the maximum height, h sub p. So for example, in our little magenta 3-block chain, here node A would simply try to create a B4 prime that extends B3. So we just try to extend the block B3. And notice that is already actually different than the strategies we were using in both of the last 2 videos. So with a 51% node, we were able to get away with just never tolerating any honest blocks in the longest chain ever. So 2 videos ago, we would have actually been trying to fork away. We would have been trying to orphan B1, B2, and B3 by forking away somewhere behind B1. Last video, where we didn't have a 51% hash rate, but we did at least have sort of tie-breaking working in favor of node A, there you did at least you gave up on all of the blocks in the honestly produced blocks on the longest chain, except for the last one. So in the last video, the strategy we considered would actually try to extend B2 with a competing block B3 prime. And here, again, because of the change in tie-breaking, that's no longer such a good idea, right? Just trying to directly extend B2 to orphan B3, because we need to actually produce 2 blocks, a B3 prime and a B4 prime, before we would orphan B3. So here, actually, in case one, we're just going to try to, node A is just going to try to extend the longest chain. It's going to try to have a B4 prime tacked on at the end of B3. The honest nodes, meanwhile, they obediently follow longest chain consensus, and they all know about, block B3, so all the honest nodes will be trying to extend also B3 to create an honestly produced block B4. So that's what's happening. All of the nodes, both sort of the node A and the other 1 minus alpha fraction of the hash rate, they're all trying to extend B3. One and only one of those 2 will succeed first. Okay, so either A creates B4 prime or an honest node creates B4. So let's talk about what happens next in each of those 2 cases. So if node A gets lucky and is the next one to produce a block, and again, that happens with probability alpha under the usual sort of random oracle assumption that we use in proof of work, if it succeeds, then it's actually going to keep that new block B4 prime private to itself. It will, for now, keep that block secret. You may be wondering what node A does next, so just hold that thought for a second. Basically, in this case, we'll transition from case 1 of the strategy to case 2 of the strategy. So I'll tell you in a second what, in case 2 of the strategy, node A is going to do. Let me just complete the description of case 1, because there is a chance that A fails in its efforts, and then in fact, the next block, and this is probability 1 minus alpha, the next block may be produced by an honest node rather than node A. And so in that case, right, we're basically still in case 1, right? So H sub S hasn't changed. There's no new secret blocks. H sub P has gone up by 1. Honest nodes extended the end of the publicly known longest chain. So we're still in case 1. So node A is just going to reset its strategy. In this case 1 strategy, it will try to extend the new end of the longest chain. Moving on to case 2. And again, case 2 is where you get if in case 1, node A successfully creates a new block extending the end of the longest chain. So like in our example, that would be if node A successfully creates the block B4 prime. And remember, is keeping it private for now. So in that case, right, so now node A has a secret block that has a height 1 higher than the maximum height of any publicly known block. That is, H sub S is now H sub P plus 1. So I've updated our running example. So in the picture in case 1, the 2 blocks in gray and they're dotted. That's meant to indicate 2 types of blocks the nodes are currently trying to create. They may or may not succeed. Those are the blocks in gray that the nodes are trying to create. So in case 2, B4 prime has turned from gray to magenta. It's still dotted. And so what that means is that in case 2, block B4 prime actually exists. It's been created. Node A has it in its back pocket, but it hasn't been publicly announced. So that's the magenta means it exists. The dotted means that it's secret, that the honest nodes don't know about it yet. Now, the honest nodes in case 2, right, they don't even know that this B4 prime was created. So from them, it still looks the same as it did before. They're still trying to extend the end of the longest chain that they're aware of, which is trying to extend B3. So the honest nodes are going to be trying to extend B3, the maximum height block that they're aware of. What's node A going to do? Well, of course, it's going to try to sort of double down on its strategy and try to extend the block it just created. It's going to try to extend, in the example, the block B4 prime. Now, one of 2 things could happen, right? With probability alpha, node A is the next one to produce a block. So in other words, B5 prime gets created next. And with the remaining 1 minus alpha probability, some honest node creates a block, which is going to be the block B4, extending the block B3. So first, let's suppose that node A succeeds and creates B5 prime. Well, node A is going to do the exact same thing it did in case 1 when it succeeded there. Namely, it's going to keep its new block, in the example B5 prime. It's going to keep that private. And then, of course, moving on, it'll keep trying to extend B5 prime with a B6 prime. And we'll see that's actually going to be in case 4. Now, if node A fails in its efforts, meaning an honest node creates a block first, that would be like B4 in our example, then in fact node A is going to stick to its guns. It's going to keep its secret block secret. It's not going to announce, in the example, what would be B4 prime, and it's going to keep trying to extend the secret block that it knows about. So in the example, it's going to keep trying to create B5 prime, even though B4, in this case, is now in existence. All right, so that's case 2. We have 2 more cases to go. And we've actually already seen how we're going to get into each of those 2 cases. So if you're in case 2 and you have success, and then in effect node A has kind of a lead of 2 over the publicly known sort of chain of honest blocks, that's going to move us to case 4. But if there's a failure in case 2, meaning that the honest nodes create a competing block at the same block height as the one private block that node A has, that's going to bring us to case 3 that we're going to describe next. So in this case, as we mentioned, node A is not going to give up on its secret chain. It's not going to give up on the block B4 prime that it already created and it's keeping secret. So in case 3, it's going to work to extend B4 prime, to extend the private block that it created back in case 1. The honest nodes, meanwhile, they're going to do what they always do. They're going to try to extend the end of the longest chain that they know about. So for example, in our running example, they're going to be trying to create a B5 extending the block B4. So let's talk about what node A is going to do if it succeeds. So like in our running example, if it actually creates its block B5 prime before honest nodes are able to create a block B5. And actually, this reminds me of something I meant to say back when we were talking about case 1, which is kind of an interesting contrast to what we're about to do in case 3. Right, so in case 1, that's when node A was just sort of extending the end of the longest chain, and the longest chain was public, everybody knew what it was. And in case 1, if node A succeeds, right? One of the things it could do with the block it just created, so that would be like the B4 prime in our example, I mean, it could just immediately announce it to everybody else. That would become the new end of the longest chain. Everybody would be trying to extend it. So B4 prime would be guaranteed membership in the longest chain if it was announced immediately. Well, here Node A is going to do something interesting, which is it's going to declare victory. So it is going to just announce its secret blocks. So like in our example, it's going to announce both B4 prime, the block that it created previously in case 1, as well as B5 prime, the block that it just created now in case 3. It's going to announce both of them. Now, maybe you're bothered that I wrote A announces both secret blocks. I mean, it's obvious in our running example that, in fact, Node A has exactly 2 secret blocks to announce, namely B4 prime that it created in case 1, and B5 prime, the block it just created just now in case 3. But actually, as we'll see in general, the only way Node A ever finds itself in case 3 is by going through this exact same sequence of events. Like first being in case 1, successfully creating one block that it keeps private, then moving on to case 2 and failing, so still having one block that it has private, and then moving on to case 3 and succeeding again, which gives it a second block. And so always in case 3, Node A is going to have exactly 2 blocks that are relevant to announce. Now, once A does announce both of those private blocks, then it is good to go. So like in the example, B4 prime and B5 prime, that's going to be the new universally recognized longest chain. Remember, the honest nodes were trying to create the block B5, but they did not yet create the block B5. So when B4 prime and B5 prime get announced, that's going to be the unique longest chain. And remember, look at the consequence at the top of the slide. That's what we needed, right? So for node A to make sure that its blocks get in the longest chain, it needs to make sure that if it ever kind of keeps some blocks private and then publishes them later, it needs to be on the unique longest chain. And that's exactly what it accomplished here in case 3. So these 2 newly announced blocks, they're guaranteed to be in the longest chain forevermore. Note also that orphans one of the honestly produced blocks, namely B4. So that definitely is a win for node A. So good things can happen for node A in case 3, okay, if it finds a block before the honest nodes. But actually, this is also the case where you see the riskiness of doing any kind of holding blocks secret, any kind of delayed block announcement. Bad things can happen to node A in case 3 as well. Because if, in fact, the honest nodes produce a block, so like in our example B5 before node A does, like the block B5 prime, now node A finds it in an even bigger hole than it was before. Previously, it was in a tie between its secret chain and the sort of, publicly known chain, and ties are broken against node A, so that was already sort of a risky position. But now, actually, the honest nodes have sort of creeped ahead. Right, so they actually have a chain which is one longer than the secret chain that Node A has been trying to create. And so at this point, Node A is just going to it's going to wave the white flag, throw in the towel. It's just going to give up and return to case 1. It's just going to say, look, I'm going to accept, that the couple honest blocks got in the longest chain. In our example, it's going to be B4 and B5. I'm going to accept, that one of my blocks got orphaned, is not going to be in the longest chain. That's the block B4 prime in the example. And I'm just going to sort of start over. Go back to case 1 and try to extend the new longest chain, which in the example would be trying to extend B5. Let's wrap up the description of the strategy with the remaining case 4. This is going to be the case where things are really good for node A, in that it has blocks that it's keeping secret with heights that are 2 or more larger than the maximum height of any publicly known block. So how do you find yourself in case 4? Well, sort of the initial way to get into it is just through case 2, right? If you're in case 1 and node A produces a block, now it has a sort of lead of 1 in effect over the honest chain. That moves it to case 2. If you succeed again in case 2, now your lead over the honest chain has grown to 2, and you find yourself in case 4. So in our example, if you look at case 2 and you look at the blockchain there, this would be if node A manages to create the block B5 prime before any honest node manages to create the block B4. So no prizes for guessing what node A is going to try to do in this case. They're obviously going to try to just double down and keep extending their secret chain. So in the example, they're going to try to create a block B6 prime, extending the still secret block B5 prime. The honest nodes, meanwhile, are blissfully unaware that blocks B4 prime or B5 prime even exist. They think the end of the longest chain is B3, so they're still trying to create a block B4, extending the maximum height block they know about, B3. If node A succeeds yet again in case 4, well, then it just gets more comfortable. Okay, now the honest nodes are even farther away than ever from ever challenging this secret chain is for dominance. So node A may as well just keep going. May as well just keep trying to extend the end of its secret chain. So like in our example, if it successfully creates B6 prime, it's again going to keep that private, and now it's going to try to create a B7 prime extending B6 prime. In other words, node A just finds itself back in case 4 yet again, this time with an even bigger gap between H sub S, the maximum height of a secret block, and H sub P, the maximum height of a publicly known block. All right, so suppose instead the honest nodes are the next ones to create a block. Well, then that may or may not take us out of case 4, right? It's just going to depend on how big the lead was that node A had with its secret chain over the publicly known chain. So, for example, if you look at our running example, so imagine that actually, node A also created B6 prime before the block B4, at which point it has a lead of 3, right? So the publicly known blocks are only B1, B2, B3, but node A also knows secret blocks B4 prime, B5 prime, B6 prime. Okay, so H sub S would be 3 larger than H sub P. And so that means that, once the honest nodes actually successfully create a B4, there's still a gap of 2 between H sub P and H sub S, so that means we're still going to be in case 4. So in that case, then node A is just going to keep doing what it was doing before. It's going to keep trying to extend the secret chain because it's still comfortable with its lead of 2 or more that it has over the publicly known chain. If, on the other hand, this new honestly produced block puts node A in the precarious position of having a lead of only 1 block with its secret chain over the publicly known chain, at that point node A doesn't want to take any more risks. It doesn't want to risk any of its sort of private blocks, its secret blocks getting orphaned. So just like in the successful part of case 3, in the unsuccessful part of case 4 where the lead shrinks to just 1, node A says, I'm just going to be safe. I'm going to publish all of my secret blocks all at the same time. Because the deepest of the secret blocks, because the maximum height of a secret block is still 1 more than that of any other block in existence, all of the honest nodes will recognize this newly public version of the secret chain as the unique longest chain. So that means the honest nodes, they have no choice. They're following the protocol. They have to extend this new unique longest chain. Node A, of course, will always extend that chain. So all of these newly announced, previously secret blocks in case 4 are guaranteed to be on the longest chain. So in our running example, this would be the case if the honest nodes produced the block B4 before node A manages to produce the block B6 prime. Okay, right, so node A has produced B4 prime and B5 prime. It went in with a lead of 2 over the deepest publicly known block B3, but if the honest nodes create B4 before node A creates B6 prime, that lead shrinks to 1, and that's going to trigger node A announcing, in this case, it's 2 secret blocks, B4 prime and B5 prime. That will have the effect of orphaning the just produced honest block B4, and will also guarantee that B4 prime and B5 prime will be in the longest chain now and forevermore. Now, unlike case 3, where we knew there were going to be exactly 2 blocks announced, that's because the only way you can get into case 3 is by going case 1, case 2, case 3, success, failure, success. Case 4, there's an arbitrarily large number of secret blocks that might be announced at this point. Like, for example, right, if you look at our running example, so now suppose actually node A managed to create B6 prime, okay, first, before the honest nodes managed to create B4. Then imagine that the honest nodes created B4. So imagine both of these gray blocks turned magenta. And now imagine that actually the next thing to happen was that the honest nodes again were the next ones to produce a block. This would be a block B5 extending block B4. So at that point, the lead will have dropped to 1, right? So there's a secret block B6 prime, but there's now a public block B5. So that would again trigger the part of the case 4 strategy where node A announces all of its secret blocks. And in that case, it's going to be 3, not 2 secret blocks, right? It's going to be B4 prime, B5 prime, and B6 prime. That's going to have the effect of orphaning both of the honest blocks, B4 and the one that was just created, B5. So that's the general principle in case 4. So at this point, node A finds itself in a position of advantage. It has a big lead, a lead of at least 2 over the honest chain. And at this point, it keeps staying in case 4 as long as it can. But as soon as there's any risk of any of its blocks being orphaned, it says, no, I'm shutting this down now. I'm just going to announce all my blocks, so to cash in my chips and make sure all of the blocks that I've produced on this secret chain are guaranteed to get into the longest chain. So that's the description of the strategy that we're going to be analyzing over the next couple of slides. Should go without saying that it is not at all obvious whether this strategy is a good idea or not. And as we'll see, it's actually going to depend on the hash rates of the node A. But if you think about it, that's already a pretty big difference from the previous video, where I claim in the last video when node A had the advantage of being able to control tie breaking, it was actually kind of obvious, if you think about it, that deviating from longest chain consensus is a good idea, kind of no matter how small of a node you are, right? Because suppose you just followed longest chain consensus, right? What happens? Well, then everybody's honest. There's no message delays, so just every block gets in the longest chain. There's no forks. So all of node A's blocks are going to get in the longest chain. All of the honestly produced blocks are going to get in the longest chain, and so node A is going to have an alpha fraction of the blocks on the longest chain. And in the last video, we saw that actually, node A had a strategy which retained the property that all of its blocks wind up in the longest chain. So it gets the same number of blocks there either way. But with that alternative strategy, you at least sometimes manage to orphan honest blocks, which means your share, the fraction of the blocks on the longest chain which are yours, are clearly going to be bigger. You have the same absolute number, and you have a strictly fewer number of other kinds of blocks, honestly produced blocks on the longest chain. With this more complicated strategy, in this more complex scenario, things are different. Things are more complicated. With this strategy, you do still sometimes manage to orphan honestly produced blocks. For example, that happens in case 3. In the successful part of case 3, right, that results in node A announcing 2 secret blocks that are guaranteed entrance into the longest chain, which also orphans 1 honestly produced block. And then in case 4, in sort of the last part of the failure mode, when the lead shrinks to 1, that again is going to lead to an orphaning of a number of honestly produced blocks. At least 1 honestly produced block, possibly more. So we see there are parts in this strategy where the honestly produced blocks do get orphaned. On the other hand, we also see there's a case where blocks created by node A get orphaned, specifically in case 3, in the failure mode within case 3. That's when node A just sort of gives up, accepts that some of its blocks got orphaned, and then just sort of restarts trying to extend the end of the longest chain. So this is why you have this sort of tug of war between these sort of 2 competing forces with this strategy, right? So sometimes it works in your favor and some honestly produced blocks get orphaned. Sometimes it works against you and some of your blocks get orphaned. And it's really not clear how that benefit analysis is going to resolve. The only option available to us to answer this question, whether this strategy is a good idea, the only option is to do some pretty non-trivial mathematical analysis. So let's get into that next.